All right, so today we will cover chapter 5 in the textbook. And chapter 5 covers probability, okay? And so probability tells us how likely or how unlikely an event is to occur. And we have, so sometimes we'll talk about the probability of some event. Okay, so we might have some event A, and we will we can talk about the probability of event A occurring. Okay, and we will say that this is the probability of A. Okay, so the probability of A is defined as PR of A. Sometimes we can also be written without the R. Okay, so you might see it presented in either form, and they're essentially the exact same thing. Okay, we have synonyms for the word probability. Such as chance and likelihood. So we can talk about, what is the chance that A will happen, or what is the likelihood of A. Sorry. I thought I would like it up here, but now I'm not so sure. Okay. And so maybe to get into the concept of probability, we first have to talk about randomness. Okay, and so we can say that the outcome of an event is random if it is unpredictable, okay, and shows no patterns. Okay, so lots of things are unpredictable, but it's only we can really only say it's random if there's no discernible patterns in it. Okay. Even though something is random, we can still come to some sense of understanding, though. Okay. Alright, so for example, well, let me allow you guys to write this down, and then I'll talk about my example here. Okay, and so, you know, for example, we can talk about a coin flip. The outcome of a coin flip is random. Or it can be considered to be random. Okay, meaning when we flip a coin, we can't really predict how it's going to land. And if I flipped a coin a bunch of times, I'm not going to see a pattern in the heads and tails. Okay, I can get a bunch of heads in a row, I can get a bunch of tails in a row, I can get heads, tails, or, you know, heads, tails, tails, whatever. Yeah, I can get a bunch of different sequences, and we're not going to see any kind of pattern in the sequence. Okay, so, you know, we cannot predict coin flips. And we will not see any pattern in coin flips. Okay. However, we still have a sense of understanding in that we can say the probability that the coin will land heads is 1/2. Okay. Okay, so we can say the probability of heads, so this is the probability that the coin lands heads, is 1/2 or 0.5. So we have that. Okay. When we talk about, in our class, we are going to differentiate between theoretic probabilities and empirical probabilities. Okay. So let me first talk about theoretic probabilities. Okay. So theoretic probabilities are going to be determined by some mathematical rules. Okay. And we will have what we call the frequentist view of probability. Which is known as the long run relative frequency. Okay, so long run meaning approaching infinity. So what we mean by that is, so, you know, if we think about this definition, what does it mean to say that the probability that a coin lands heads is 1/2? What exactly does that mean? Okay, well, you know, 1/2 is 50%, but, you know, what does it mean to say, you know, that the likelihood that the coin will land heads is 50%, or that the chance that a coin, you know, coin flip lands heads is 1/2? You know, what do you think it means?
Half the time though it could be tails or it could be heads. 50-50.
So, and it's not, it doesn't mean that half the time I flip a coin, it's going to land heads, okay? because I could flip a coin 10 times and I won't necessarily get 5 heads and 5 tails. Okay, so but what we're looking at is the long run relative frequency. Okay, so if I were to flip the coin an infinite number of times, so if I flip a coin 1,000,000 times, I should get something very close to a half. I'm not going to get exactly 500,000 heads and 500,000 tails, but I should get, you know, maybe 500,000 and a few, okay? Or 499,900 something, okay? I should get something close to 0.5, but maybe not exactly that. The idea here is that if we were to flip it, you know, close to an infinite number of times, which is not physically possible, but, you know, in our theoretic minds, if we were to do that, then the relative frequency of getting heads should be close to 0.5, or should be 1/2. Okay, so that's what we mean. So, you know, if we flipped the coin an infinite number of times, the relative frequency of heads would be 0.5. Okay, which is, you know, not possible in reality. The relative frequency of heads would be 0.5. Okay, but you know, for any actual number of coin flips, it will not necessarily be exactly 1/2. Okay, and so those are theoretic probabilities. You know, they're based on mathematical rules, so it's kind of, we've arrived at the number 1/2 because we've said, hey, I've got a coin, both sides should be equally likely. I've got two sides, and if they're both equally likely, then the probability that it'll land on one of the sides is 1/2. Okay. On the other hand, we have empirical probabilities. Okay, so empirical probabilities, these are based on actual data or you know, actual experimental trials or simulations. So probabilities based on actual experiments or simulations. Okay, so let's say you are an alien, you've never seen a coin before, you don't quite understand how physics works, okay? But you observe, you know, you see people flipping coins to do something, okay? And so your alien overlord says, I want you to investigate coin flips. Tell me, what is the probability that the coin will land heads, okay? So you don't know anything about physics, so what you do is you say, well, I have obtained one of these coins, and we're going to try flipping the coin a bunch of times. So maybe you flip the coin 1,000 times, okay? So, all right, so we'll say, you know, pretend, okay, we have never seen a coin before. Okay, we barely understand, we don't really understand physics. Okay, but we want to know the probability that it will land heads. And so what we will do is, we actually flip the coin 1,000 times. Okay, and let's say it lands heads 491 times. Okay, so our empirical probability is equal to 491 divided by 1,000, or 0.491. So this is our empirical probability. And what this means is we would say, we estimate that the probability a coin will land heads is 0.491. Okay? And that's empirical probability. And it sounds silly to do something like this for a coin flip, because coin flips are probably the most basic form of chance that we're exposed to, even from childhood. We flip coins and we try to guess that. But this is often useful in situations where math gets really complicated or math doesn't even exist. Okay, so for example, if you want to predict the outcome of a basketball game, okay, so right now it's the NBA playoffs, and teams are competing, and you have all of these sports websites and channels talking about who's going to win and things like that. Sometimes they'll say this team has a 60-something% chance of winning, 62% chance of winning, and the way these numbers have been figured out isn't that there's some formula that you can just say, oh, this player plays for the team, and there's no formula like that exists. However, there is a computer simulation based on certain mathematical understandings of the game, but basically a computer simulation of the game, and the computer plays games against itself. And they have the computer play maybe 1,000 games against itself, and maybe in those 1,000 games where the computer pitted, one team against the other, perhaps one team won 62% of the games out of those 1,000. Then it will say, we estimate the probability that team whatever wins to be 62%. Okay, so a lot of times for sporting events, and you see these probabilities or point spreads or whatever, those are based on empirical probabilities. Okay, we don't have there's no mathematical formula that you can just say, hey, this team is playing this team, what's the probability? Okay, we have computer simulations set up, and we just run thousands of these to predict it. Okay, and so if anybody who has played sports on a video game system can probably has seen probably a computer play against itself. Okay, and it's basically instead of just doing it one time, you're having the computer do it thousands of times. And of course, how good of the prediction, that depends very much on how good the simulation is of reality. And so, as time has gone on, the simulations have gotten better and better. But essentially, we're still just performing empirical probabilities here. Okay. And so we have empirical probabilities and we have theoretic probabilities. And what we have is that we have something called the law of large numbers. And that states that if you're looking at empirical probabilities, if you do it more and more and more times, the empirical probability will approach the theoretic probability. So as you perform more and more random trials, the empirical probability should approach the theoretic probability. Okay, and so this is how casinos stay in business, or how the insurance industry stays in business. Okay. Casinos are have their games designed in such a way to maintain what they call a house edge, so that the casino is favored to win more than it loses. But of course, because they're games of chance and there's randomness, any player at any time could come out ahead. You know, you could play just a few games of roulette or whatever it might be, some game of chance, and you could win and walk away with a few extra bucks. Okay, but over the course of a day or a year or whatever, you know, with thousands and thousands or millions of players playing these games of chance, the law of large numbers favors the casino side, because what it says is that the outcome of all of these real-life trials, the empirical probabilities, will approach the theoretic probabilities. So maybe in the short run you can come out ahead. You know, maybe you're quote lucky over your lifetime and you still come out net positive, but overall, looking at across all people, all time, the casino will maintain their edge. Okay, and the same applies for insurance. You know, when you buy car insurance or health insurance or whatever it is, those premiums that are calculated, those are calculated based on the law of large numbers. So sure, maybe you could get in multiple accidents in 1 year, okay, and cost the insurance company hundreds and thousands of dollars, but the insurance premiums, you know, across everybody, adds up in such a way that that the insurance business can remain viable. Okay, and there's nothing unethical about the way insurance companies run. They certainly offer a necessary financial instruments to prevent you from financial ruin in certain unforeseen events. But like any other business, they need to stay in the positive. So okay, so let's so our class will focus mostly on theoretic probabilities, calculate these mathematical rules that go into theoretic probabilities. So we'll get started there. Okay, so we'll say rules for finding theoretic probabilities. So rule one, number one, is that all probabilities are between 0 and 1, inclusive. So, you know, for any event A, we will say the probability of A is in between 1 and 0. Okay, so this is basically saying, are you guys okay with this notation here? This basically means that probability of A is greater than or equal to 0, and also less than or equal to 1. And we often write probabilities in this notation where we say 0 is less than or equal to the probability of A, less than or equal to 1, to kind of form some boundaries of our probabilities. Okay. We also have something called complements. So complement is spelled with an E, coming from the same root as the word complete. Okay, and so the complement of A is the event where A does not happen. Okay, and so together A along with its complement forms all possibilities, okay? Because in life, either something happens or it doesn't happen, and there's no other possibility, okay? Whatever it is that we're talking about, okay? The coin, I can flip a coin and it's either going to land heads or it's not going to land heads. And that covers every possibility, okay? Either, I don't know. Whatever it is we're talking about, you know? That door could burst into flames in the next 10 minutes, or it's not, okay? Those are the only two possibilities. Either something's gonna happen or that thing is not gonna happen, okay? I certainly hope it doesn't burst into flames in the next 10 minutes. That would be quite terrifying. But either that's going to happen or it's not going to happen, okay? And so what we say is that we denote the complement of A is written as A with a C to indicate A complement. It can also be written as kind of not A. And we will say that the probability of A plus the probability of basically not A, these two things add up to 1 to indicate that they encompass all possibilities. Okay? And what this basically says is that the probability of not A is equal to 1 minus the probability of A. Yes, question?
So I could further understand that, maybe draw a couple examples.
Sure. Okay, but do we have all of this written down here? Okay, so for example, here let me do the next rule, and then we'll talk about all of these things. Okay, and then let's talk about simple outcomes. Okay.
Is that rule 3?
Yeah, this will be rule 3. Okay, so for simple outcomes are outcomes where each outcome is equally likely. So outcomes that are equally likely. Okay, and so, if we have some event A, then the probability of A is equal to the number of outcomes in A divided by the total number of outcomes. Okay, and then just make sure you underline this equally likely. Okay, this only applies if the outcomes are equally likely. If they're not equally likely, this doesn't work. All right, so here we'll do a few examples to kind of illustrate all of this stuff. Okay. I'm hoping you guys are familiar with a deck of cards. Let me pull up an image of a deck of cards here. Okay. right, so here I've got a deck, 52 cards, okay? These are clubs, spades, hearts, and diamonds. Okay, and so with a deck of cards, if we shuffle them up and draw one card, each of these cards have an equal chance of being selected, right? So I could just ask something as simple as, what is the probability that a randomly selected card is the ace of clubs? Okay, and so our answer there is that, well, there's only one card that counts as the ace of clubs, and there's 52 possible cards, and so I have a 1 out of 52 chance that a randomly selected card is the ace of clubs. So far, so good? Okay. All right. Question 2. What is the probability that a random card is not the ace of clubs? Okay. So this would be an example of the complement, right? So not the ace of clubs would be the complement of the ace of clubs, okay? And so we can kind of see this already and say, okay, well, there's 51 cards that aren't the ace of clubs, so it's going to be 51 out of 52. We can also say the probability of not ace of clubs is equal to 1 minus the probability of ace of clubs, which is going to be 1 minus 1 over 52, and that also gives us 51 out of 52, right? We all know how to add and subtract fractions, I hope. Yes?
How come the coins it wasn't like 1 out of 2?
It was 1 out of 2. Or, wait, what are you talking about?
How do we get the other number, like the fraction? This is way before. Never mind. I should
Okay.
ask Ed.
With the coins?
Yeah, because we got that fraction like point. I think I got lost in that.
0.5?
0.491.
Yeah.
0.491? Oh, that was an example where I said,
Oh, how many times?
like, that was an example of empirical probability where I flipped the coin. I said, let's pretend I flipped the coin 1,000 times. And now anything could have happened, but I'm just saying, let's say that the coin landed heads 491 times, okay? Now it could have, now if one of you flipped a coin 1,000 times and you counted how many times you got heads, you could have gotten a completely different number too. Okay, I'm just saying, let's pretend I got 491 heads, and in that case, my empirical probability, which is the relative frequency I observed, is 0.491. Okay, that's how we try to, we run simulations to try to estimate probabilities if it's too complicated to do the math here. Okay, in this situation, it's quite easy to do the math, and we do this. Okay. All right. So is this okay for I don't know, complement rules and stuff? Okay, let's just try a few more of these. Okay, so here again, the deck of cards for your reference. And I'm going to ask, what is the probability? So all of these, it's like, if I pick a random card, or if I pick a card at random, what is the probability the card is ... So I'll say is a spade. Okay, so don't shout out your answers, just write your answers. Is an ace. Face card. Say not an ace. And not a face card. So face card would be Jack, Queen, and King. Okay? Aces are not face cards. There's no face on an ace. It's a high value card, but not a face card. Okay, so go ahead and answer these questions. Should just take you a brief minute or two, and we'll go over the answers here. Okay, so let's go over our answers. What's the probability that a card is a spade? 13 out of 52, or that simplifies to 1/4, which further simplifies into decimal, if you want to turn them into decimals, into 0.25. Okay, an ace,
113.
so 4 out of 52, which simplifies to 1 out of 13. And in decimal form, 1 out of 13 is 0.0769. Okay, a face card. Yeah, so there's 12 cards in the deck that are face cards. So 12 out of 52, which simplifies to 3 out of 13. And that would also be 0.2308. In decimal form. Okay. Not an ace. Yeah, okay. So here we would have 48. So this would be 1 minus our answer for ace. So 1 minus 1 out of 13, which would give us 12 out of 13. Okay. And that's 0.9231. Okay. And not a face card, we would do 1 minus 3 over 13. 10 out of 13. And that is 0.7692. Okay. Good? Just want to make sure everyone's all right. Okay. So carrying this further, we can talk about combining events with and or. Combining. Okay, so I'm going to first start off with or, okay? Okay, and in statistics, when we use the word or, it's always an and or. Okay, and what I mean by this, and you know, or doesn't have to be all caps, it could just be written the regular way. When we, in English, we have, there's an ambiguity with our language in that we only have one word for or, okay? And sometimes we mean them in different ways, okay? And we generally pick this up from context, but the same question can be asked. Yeah, I could use the same words, okay? So here, I'm gonna write the same question twice. Okay, so if I ask you, do you like chocolate or vanilla ice cream? Do you like chocolate or vanilla ice cream? You would tell me or vanilla or something like that, right? Your answer would be, you know, I like chocolate, or whatever. Here, your answer could be chocolate. Okay? Or vanilla. Okay? What if I ask the question, do you like chocolate or vanilla ice cream?
Yes.
And your answer would be yes or no. Okay? All right, and so it's the exact same question, but the meaning of the word or is different. And so we are always, in statistics, we're always referring to this one, okay? This is the or we use in statistics. Okay, which is kind of an and or, also called an inclusive or. Okay? Whereas the or over here is what we call an exclusive or. Okay, where we're expecting you to tell me chocolate, or you're telling me vanilla, or something like that. I don't know if this distinction makes sense to you guys. But so in statistics, we're always talking about the inclusive or. Okay, do you like chocolate or vanilla ice cream? And you're supposed to answer yes or no. Okay, and so when we talk about the or, we often, you know, draw a little Venn diagram here, okay? Okay, and we can say, you know, what is the probability that someone likes chocolate or vanilla ice cream? So what is the probability that of chocolate chocolate or vanilla? Okay, the answer here includes everyone who likes chocolate, everyone who likes vanilla, and everyone who likes both. Okay, so this is everyone who likes chocolate, likes vanilla, and likes both. Okay, so mathematically, this turns into probability of chocolate plus probability of vanilla. Okay, but then we do a funny thing. We subtract off chocolate and vanilla. Okay, now why am I subtracting off both? Okay, well, if you think about what is the shape that we are getting here, it looks something like this. This is the shape of this thing here. That's the shape I want to get. Okay, kind of this joint double circle, looks like the MasterCard logo without anything inside. Okay, and basically what I'm doing is I'm taking the chocolate circle, I'm taking the vanilla circle, but if I added two circles straight up, the total area there is going to be more than like the MasterCard sign, right? Because and the difference there is because I've double counted the little piece of overlap. Okay, so what I have to do is I have to subtract that off. All right. Is that okay? Okay, and so let's try this out with our deck of cards here.
Can I just ask something?
Yeah.
The PR, was that the same as the P?
Yeah, the PR, yeah, sorry, PR and P is the same thing, okay? Probability of whatever, okay? All right, so I could ask, you know, so we've already asked this question. What is the probability of clubs? What is and we said the answer there is 13 out of 52 or 1 out of 4, right? Okay, and we said, what's the probability of a face card? And we said that was 12 out of 52, right? Or 3 out of 13. Okay, so I could ask, what is the probability of clubs or face card? Okay, so just take a second here. Clubs or face card? All right. So take a brief moment to figure this out. I guess I should put the general form. So the probability of A or B. So last time I had probability of chocolate or vanilla. This is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so in the picture it was circle plus circle minus the little overlap. Okay? Oh, I meant 13 out of 52. Thank you. That's a typo. Okay. So take a second to figure this out. Okay, so the answer is 22 out of 52, and that simplifies to, what does it simplify to? 11 over 26, or 0.4231. Okay, now how did I get that? Okay, well, there's a few ways to do this. So here, probability of clubs or face card, okay? Probability of clubs basically is all of these cards count as clubs, right? How many do I have? I've got 13, okay? So I can do probability of clubs. So I'm going to do probability of clubs plus probability of face card minus probability of the overlap, right? Clubs and face card. Okay, so clubs, I've got 13 out of 52. Okay, so all of these ones, these are all, those are all clubs. Okay, now let's do the face cards. Okay, how many face cards do I have? I've got, let me get a, I need a thicker pen here. Oops. Okay, so these are my face cards, and I've got 12 of them. Okay. Okay. But if I do 13 plus 12, that'll be 25. But the thing is these ones right here overlap. Okay, so I have to subtract off those. Okay, otherwise I would have double counted those. And here I get a total of 22 out of 52. Okay. Also, you know, we could have just said, okay, well, all of these cards are going to be clubs or face cards. I could have gone through and counted these. I could have said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then said this is 14. Maybe I need my thicker pen again. Okay, this is 14, 15, 16, 17, 18, 19, 20, 21, and 22. I don't know if you guys can read those. But here I have a total of 22 cards that fit the description, clubs or face card, okay? And so we can see that indeed this gives us the correct answer of 22 out of 52. Yes, question?
Say you don't have this layout in front of you.
Uh-huh.
Say you don't have a picture in front of you, but you already have those two answers, the clubs and the face card.
Correct.
How would you know it's overlapping? How do you know you're subtracting the
Yeah, okay, so someone else could ask the question, what is the probability of clubs and face card? Okay, and you would have to have some knowledge of a deck of cards in order to answer this. But you would say, well, how many cards are there that are clubs and face cards? And you'd say there's the Jack of clubs, the Queen of clubs, and the King of clubs. So this would be Jack, Queen, and King of clubs. There's only 3 of them, so we would say 3 out of 52. And then you have all of the pieces you need. You have 13 out of 52, 12 out of 52, and 3 out of 52. And you would add these 2 together, but subtract this one off to get 22 out of 52. Is that okay? All right, let's just try this out one more time here. This time I'm going to set it up a tiny bit differently. Okay, I'm going to say you surveyed 200 people. Okay, you surveyed 200 people. We're going to say 90 own a dog, 70 own a cat, 30 have both cat and dog. Okay, so my question here is, if we select a person at random, what is the probability? No, there's 200 people, okay? What is the probability that the person has a cat or dog? Okay, so take a minute to answer that question. Okay, so our answer is 0.65 or 13 out of 20, okay? So this is our answer, 13 out of 20, 0.65. All right, so let's just look at this, right? So the question is asking, what is the probability of cat or dog? Okay, question.
On a quiz, are we going to be dealing with decimals or fractions?
Be prepared to deal with either, okay? So, I mean, you got to be comfortable with both, okay? So if you see things in fraction form, you got to be okay with that. If you see things in decimal form, you got to be okay with that. So it's going to be multiple choice, so look for the right answer, right? Okay, so probability of cat or dog, this is going to be probability of cat plus probability of dog minus probability of cat and dog. So we got 70 out of 200 plus 90 out of 200 minus 30 out of 200. When you do all of this, you get 130 out of 200, which simplifies to 13 over 20, or 0.65. Yeah, question?
What about, I just don't understand, because if you survey 200 people,
Uh-huh.
90 of them own a dog,
Yes.
70 own a cat,
Yes.
30 have both cat and dog.
Yes.
What do those 10 others have? Just
There's no 10 others. There's nothing here. We'll turn this into something else here, okay? I'll get to that. But there is no 10, okay? 10 doesn't come anywhere, because these 90 include these 30, and these 70 include these 30 as well, okay? Okay, these 90 people who own a dog, they include these 30 people who have both a cat and dog. Or I should say, these 30 people who have both a cat and dog are counted in this number of 90 people who have dogs. And they're also counted in this group of 70 people who have cats. Yeah.
So they're the overlap.
They are the overlap, yes. Yes, okay?
We see the light now.
Yeah, okay, yeah. Yes?
It's a little ambiguous, though, because we don't know how many circles they want.
How many circles?
Yeah, like if someone has a circle in choice, we would have to know they could answer
I guess so you know we're surveying people, and then I guess the survey has to look like this, right? Like, do you own, or like check what you own, right? Do you own? Anyway, this don't write this down, but and it'll be like this: dog, cat, mouse. I don't know. Okay, and then people are checking off. You know, I've got both dog, cat, and mouse, and we are like the happy household of animals or something. You know, I don't know. Okay, guinea pig, whatever other, you know, a bird, parakeets. I have no idea, right? This is like Petco's survey or something, or what's the other? PetSmart. What other? Lots of pet stores out there. Okay, now we could even further ask and just say like, and this one would be a little bit tougher. So if I use the same information, and I'll just give you the answers here, but you know, you should be comfortable with this line of thinking as well. So we're going to take the same thing. Survey. You don't have to rewrite this. Surveyed 200 people. Okay. And what if the question is, you know, I select someone at random. I select a random person from our 200. Okay, what is the probability this person has a cat and no dog? Okay. Okay. I'll just let you think about this for like 10 seconds, and if you get it, great, awesome, like kudos to you, and if you don't, I'm going to give you the answer. Okay, so anybody have an answer here? 40 out of 200, that is correct. Okay, so 20%. 40 out of 200 have a cat and no dog. All right, so how do we get that? Okay.
730 from the
Right. Ah, okay. So some of you are like, and then others of you got it. Okay, so I'm going to make a table. Okay, so our 200 people can either be split into those who have dogs and those who do not have dogs. Okay, then that's it. That's one way to split the 200. Okay, the 200 people can also be split into people who have cats and those who do not have cats. Okay, and we are given, we say the total number of people with cats is 90, and the total number of people with cats is 70, and the total number of people with dogs is 90. Okay, and we have one other number, and the 30 goes right here. This is the people who have dogs and cats, right? Okay, so these are the 4 pieces of information given here. We can fill in the other information, right? So if this is 70, what number has to go right here so it adds up to 200? 130. Okay, what number has to go here? 110, right? Okay. And if 30 have dogs, how many don't have dogs? Right? Because these two numbers have to add up. And what has to go here to make this 60? And what has to go here so these add up? 70. So all of these other ones add up. Okay? And so this question, if I select a person at random, what is the probability this person has a cat and no dog? That's this group. That's going to be 40 out of 200, which is what we have right here. Okay? 40 out of 200. And all of these other questions can also be answered, right? Has a dog and no cat. And our answer there would be 60 out of 200, or 0.3. Okay? And this will be has no dog and no cat. No dog and no cat. 70 out of 200. So don't just say 70, okay? Because we're talking about probabilities here, so it's always 70 out of 200, 0.35. Okay? Is this okay with everybody? Great. Okay. So that covers, or we have this concept of mutually exclusive events. Okay. Mutually exclusive. You know what? Let's take a break.